Jupiter, the largest planet in our solar system, is a celestial giant. It's a gas giant, composed mainly of hydrogen and helium. Jupiter's immense gravity holds a fascinating collection of objects in its orbit. Among these are its many moons, a diverse and intriguing family numbering at least 95. These moons vary greatly in size, composition, and history. They offer scientists valuable insights into the formation and evolution of planetary systems. Jupiter's moons are a testament to the power of gravity. They showcase the diversity of objects that can exist within a single planetary system. Some are large and round, resembling planets in their own right. Others are small, irregularly shaped, and likely captured asteroids or comets. The study of these moons provides a unique window into the processes that shaped our solar system and others. Among Jupiter's many moons, 4 stand out as giants in their own right: Io, Europa, Ganymede, and Callisto. These celestial bodies are not just any moons, they are the largest and most intriguing of Jupiter's 79 known moons. Each one of them has unique characteristics that make them fascinating subjects of study for astronomers and scientists alike. These are the Galilean moons, named after their discoverer, the Italian astronomer Galileo Galilei. Galileo's discovery in the early 17th century marked a pivotal moment in the history of astronomy. His observations challenged the long-held belief that all celestial bodies revolved around the Earth. In 1610, Galileo observed these moons through his telescope, a discovery that revolutionized our understanding of the cosmos. His findings provided concrete evidence that not everything in the universe revolved around the Earth, thus supporting the heliocentric model proposed by Copernicus. It provided evidence that not everything in the universe revolved around the Earth, challenging the prevailing geocentric view. This was a monumental shift in perspective, leading to a broader understanding of our place in the cosmos and paving the way for modern astronomy. The Galilean moons are a fascinating study in contrast. Each moon has its own unique environment and geological features, making them distinct from one another and from other moons in our solar system. Io, the innermost, is a volcanic world, constantly erupting with molten sulfur. Its surface is dotted with hundreds of volcanoes, some of which are the most active in the solar system. The intense volcanic activity is driven by the gravitational pull of Jupiter and the other Galilean moons. Europa, encased in ice, is believed to harbor a vast subsurface ocean that could potentially support life. The ice-covered surface is crisscrossed with cracks and ridges, hinting at the dynamic processes occurring beneath. Scientists are particularly interested in Europa because its ocean might have the right conditions for microbial life. Ganymede, larger than the planet Mercury, is the largest moon in our solar system and possesses its own magnetic field. This magnetic field is unique among moons and suggests a complex internal structure, possibly including a liquid iron or iron sulfide core. Callisto, the outermost of the 4, bears the scars of countless asteroid impacts, a testament to its ancient history. Its heavily cratered surface is one of the oldest landscapes in the solar system, providing a window into the early conditions of the outer solar system. Io is a world of fire and brimstone. It is the most volcanically active body in our solar system. Hundreds of volcanoes dot its surface, spewing lava fountains that can reach tens of kilometers high. These eruptions are a result of the intense tidal forces exerted by Jupiter and its other moons. Io's interior is constantly being stretched and squeezed, generating heat that melts rock and fuels its volcanic activity. Io's surface is a kaleidoscope of colors, a testament to its volcanic nature. Yellows, reds, oranges, and blacks paint the landscape, reflecting the presence of various sulfur compounds. These compounds are constantly being recycled through Io's volcanic activity, creating a dynamic and ever-changing surface. Io's atmosphere, though thin, is composed primarily of sulfur dioxide, a direct result of its volcanic outgassing. Europa is a world of ice and mystery. Its surface is a smooth, icy shell, crisscrossed by a network of dark lines and cracks. Scientists believe that beneath this icy exterior lies a vast global ocean of liquid water. This ocean, potentially containing more water than all the oceans on Earth combined, is thought to be heated by tidal forces similar to those that drive Io's volcanism. The possibility of a subsurface ocean on Europa has captivated scientists for decades. Water is considered a key ingredient for life as we know it, The presence of a vast, potentially habitable ocean on Europa raises the tantalizing possibility that life may exist elsewhere in our solar system. Scientists are eager to explore this ocean, searching for signs of life in this alien environment. Section 5. Ganymede, King of the Moons. Ganymede is a world of superlatives. It is the largest moon in our solar system, even larger than the planet Mercury and the dwarf planet Pluto. It is the only moon known to possess its own intrinsic magnetic field, a testament to its active interior. Ganymede's surface is a mixture of old, heavily cratered terrain, and younger, brighter regions marked by grooves and ridges. Ganymede's internal structure is also unique. Unlike most other moons, Ganymede is differentiated. This means its interior is separated into distinct layers, likely a metallic core, a rocky mantle, and an icy shell. This differentiation suggests that Ganymede experienced a period of internal heating early in its history, possibly due to radioactive decay or tidal forces. Section 6. Callisto, a cratered time capsule. Callisto is a world of ancient impacts, a celestial body that has witnessed the violent history of our solar system. Its surface is the most heavily cratered of any object in our solar system, a testament to its long and violent history. Each crater tells a story of a collision, a moment frozen in time. Unlike its more active siblings, Callisto shows little evidence of geological activity, suggesting that its surface has remained largely unchanged for billions of years. This lack of geological activity means that the surface we see today is almost the same as it was eons ago. This makes Callisto a valuable time capsule, preserving a record of the early solar system. Scientists study its surface to understand the conditions and events that shaped our cosmic neighborhood. Callisto's dark surface is thought to be composed of a mixture of rock and ice. This unique composition provides clues about the materials present in the outer solar system during its formation. Its interior is likely a mixture of ice and rock, with a possible small, rocky core. This combination hints at the processes that occurred during its formation and the subsequent evolution of the moon. Unlike Ganymede, Callisto is not differentiated. This means that its interior did not separate into distinct layers of rock and metal. This suggests that Callisto never experienced the same level of internal heating as its larger sibling. The lower internal heating prevented the differentiation process, leaving Callisto with a more uniform interior. This lack of internal heat may explain Callisto's relative lack of geological activity. Without significant internal heat, the moon's surface remained static, preserving its ancient features. Section 7. Beyond the Giants, a Myriad of Moons. Beyond the Galilean moons, Jupiter hosts a vast collection of smaller satellites. These moons are diverse in size, shape, and origin. Some are likely captured asteroids or comets trapped by Jupiter's immense gravity. Others may be remnants of larger bodies that were shattered in collisions early in the solar system's history. These smaller moons, though less well known than their Galilean counterparts, are no less intriguing. They offer scientists valuable clues about the processes that shaped the early solar system, the dynamics of planetary rings, and the complex interplay of gravity and orbital mechanics. Section 8. Exploring the Jovian Realm. The exploration of Jupiter and its moons has been a cornerstone of planetary science. This gas giant, with its swirling clouds and immense magnetic field, has captivated scientists and astronomers for centuries. The quest to understand Jupiter is not just about the planet itself, but also about its diverse and intriguing moons. From the early flybys of the Pioneer and Voyager spacecraft to the dedicated orbits of Galileo and Juno, each mission has revealed new insights into this complex and dynamic system. The Pioneer missions in the 1970s were the first to provide close-up images of Jupiter, while the Voyager missions expanded our understanding of its moons and magnetosphere. These missions have provided stunning images of Jupiter's swirling atmosphere, its Great Red Spot, and its intricate ring system. The Great Red Spot, a massive storm larger than Earth, has been observed for over 300 years, and its mysteries continue to intrigue scientists. They have also returned valuable data about the composition, structure, and evolution of its moons. Each moon, from volcanic Io to icy Europa, presents a unique environment that could hold clues to the formation of our solar system. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in 2023, will further our understanding of Jupiter's icy moons. This ambitious mission aims to explore the subsurface oceans of these moons, which could potentially harbor life. JUICE will spend several years studying Ganymede, Callisto, and Europa, searching for signs of life on these potentially habitable worlds. The mission will use a suite of scientific instruments to analyze the surface and subsurface of these moons, looking for evidence of water, organic molecules, and other indicators of life. This mission represents a new chapter in our exploration of the Jovian system and the search for life beyond Earth. As we continue to push the boundaries of space exploration, the data and discoveries from JUICE will help us understand not only Jupiter and its moons but also the potential for life elsewhere in the universe. Section 9. The quest for life continues. The moons of Jupiter, particularly Europa, hold the tantalizing possibility of harboring life. The search for life beyond Earth is one of the most profound scientific endeavors of our time. It challenges our understanding of our place in the universe and raises profound questions about the nature of life itself. The upcoming Europa Clipper mission, set to launch in 2024, will be dedicated to the study of Europa. Equipped with a suite of scientific instruments, Europa Clipper will investigate the thickness and composition of Europa's icy shell, search for evidence of plumes erupting from its ocean, and characterize its subsurface environment. The data returned by this mission will be invaluable in assessing Europa's habitability and guiding future missions to search for signs of life in this alien ocean.